Oh, geez. Am I up here? Okay, hello, everybody. Hello! I'm really, really excited to be here today. I'm so excited to give a 40-minute long Ignite-style presentation, which was the slide I was going to put in here, but my tethering is too slow, so I'm just telling you the joke instead of putting it in slide form. Imagine that there is an Ignite slide here. Okay, so I'm wearing this hamburger hat today because I heard I needed to dress up, wear my formal attire. So, but I'm going to take this off now because I feel it's probably bad for the recording. I don't want my face to get all dark and stuff. So, hello everybody, hamburger hat. So we're going to be talking about a compacting GC for MRI today in Ruby 2.7. Hello. 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 I apologize. I know this is the third day. We're nearing the end of the third day, and you have come to an extremely technical presentation, so my apologies. My name is Aaron Patterson. My given name is Tenderlove. Changed my name to Aaron, so you can call me either one of those. If you don't recognize me here, this is what I look like on the internet. I have two cats. This one's name is Gorbachev Puff Puff Thunderhorse. He is the most famous of my cats, and I have stickers of him. If you'd like a sticker of my cat, please come say hello to me. This is my other cat. Her name is SeaTac, Airport, Facebook, YouTube, Instagram. All right, I'll finish it. So I am extremely nervous in front of all of you all today, but actually I stayed at a Holiday Inn Express last night. This is a true story. Here is me at the. I'm on the Rails core team. We're the team responsible for developing Rails, and I looked up my commits. And my first commit was here in 2009, so I've been a committer for, well, my first commit was about 10 years ago, but I've been on the core team since 2011. I'm also on the Ruby core team, which is responsible for developing Ruby, and my very first commit to the Ruby core team, or to the Ruby core, was 10 years ago in October, so this is my 10-year anniversary on the Ruby core team. Thank you. Now, this is not to say that I know what I am talking about. That is absolutely not true. So I need you to take your expectations of this presentation. I need you to lower them a little bit for me. And then when they are down here, just bring them down just a little bit more for me. I really appreciate that. So the way that I actually got onto the Ruby core team is I was able to crash Ruby a whole lot. And I got a lot of seg faults, and those produced core files, and they were Ruby core files. Now, all of you may actually already be on the Ruby core team. What you should do is you should go do ls and /cores. You might also have many Ruby core files as well. So today I'm going to be talking about compacting GC for MRI. But before I do that, I want to talk about some controversial features in Ruby 2.7. Matt's talked a little bit about these in his presentation, and I want to talk about them too. The first one is the pipeline operator. Unfortunately, this got deleted, but I want to talk about it a little bit anyway. It looks like this. And I know that there was a lot of controversy around this. People did not like this operator, well, implemented in this way. But I thought to myself that Ruby is designed for developer happiness, as Matt says. So I decided what I would do is I would change the pipeline operator to a smile operator instead. And you can actually go see this pull request here, so it's up there. Unfortunately, it got rejected, and I think that's because the pipeline operator was canceled, so that's unfortunate. We could have had emojis in there, but we do not. Now, the next thing I want to talk about is typed Ruby. How many of you are excited about getting types into Ruby? Yeah, all right, that's great, that's great. But the thing that I don't really understand about it is I thought that we already typed Ruby. I know some of you may copy and paste from Stack Overflow, but we typically type things, so. All right, let's actually get down to what we're supposed to be talking about today, which is manual heap compaction for MRI. This is a patch that I wrote for Ruby, and it's in Ruby now. It took me about 3 years to complete this work, and I have to admit this is the most difficult project I've ever worked on in my life. This is the most difficult thing I've ever written in my life. And I usually don't say that I have any new ideas. Like, I'll give presentations and I'll say I don't think of anything new, but I think I finally had like a new idea, and that's this one, and I'll show you how I know this. Actually, Chris Seaton tweeted this. He is on the Truffle team. You may have seen him around the conference. He said that I had a novel solution for not moving objects referenced from C. Now, Chris he comes from an academic background, so I want to translate this slide a little bit, or this tweet a little bit for you. So when Chris says novel solution, what that actually means is that I am a genius. So. So thank you so much. So I want to do, like, before we get into the meat of this, really, I do want to say a quick couple of thank yous. I want to call out a couple people specifically to thank, and that is Koichi Sasada and Allison McMillan. And I want to thank them because, well, I'll tell you why. When I very first came up with this project, for many years, I kept thinking to myself, oh, it's impossible to move or get compaction implemented in MRI. And I just thought that was a thing that couldn't be done. And I explained this to Koichi at RubyConf 3 years ago or so, and he said to me, well, why not? Why is it impossible? And I said to him, well, I don't know, just many smart people tell me that. And he said, well, maybe you should try it and see if it actually is. And I was like, okay. So then I tried it, and it is possible. But unfortunately, it took me a very long time to implement this, and it was, as I said, this was the most difficult project I've ever worked on, so I would get stalled and kind of depressed about it. And Allison reached out to me and said, hey, I would like to work with you on this project. So every week I would pair with her on this, and that meant that I had, like, I don't particularly like pairing with people when it's just me staring at some really not great C code, trying to figure out what's going on. So each week I would try to figure out what we were going to do, plan it, and then actually do that pairing session. So she helped me move this project along, and it wouldn't be here today without these two people. So today's topics. I'm going to talk about Ruby's heap, the compaction algorithm, implementation details, results, and if we have time at the end, I'm going to talk about debugging techniques. I think a lot of people talk about GC algorithms and implementations, but I don't think they talk about debugging garbage collectors, and I want to talk about that if we have time. So what is compaction? Compaction is basically taking allocated memory and free memory and rearranging them. So imagine that we have memory that looks like this with allocated memory interspersed with free memory. We can rearrange it to look like this so that all of the free memory and allocated memory is next to each other, and we can combine those blocks together to be something like this. Now, this may, like, maybe some of you remember this. This is defragging a hard drive, but instead of defragging persistent data, like data persisted to a hard drive, instead what we're doing is defragging data that's in memory. Now, one question is, why would you want to do this? What is the benefit of compaction? One benefit is efficient memory usage. So let's say, for example, we have a heap layout that looks something like this, and we want to allocate something. We want to allocate a new chunk of memory. So we say, oh, I'd like to allocate this, but unfortunately, that chunk that we would like to allocate, it's too wide, so it won't fit in this free area. So maybe we look at this free area, and well, it won't fit there either. It won't fit in either of these two places, so we'll get an out-of-memory error. We can't allocate this chunk. Now, if we had compacted this heap, we would actually have enough room to allocate that amount of memory. It's wide enough, so we can allocate into that chunk. So we're able to use this memory more efficiently. Another reason that we might want to compact is better, more efficient use of CPU caches. So let's say when a program reads memory, it has to go through the CPU to get that memory. So it has to read some memory, and in order to do that, the CPU has to go ask your RAM for it. Now, the CPU will read chunks of memory at a time, and actually reading from the RAM is kind of a slow operation, so there are a few caches in between the CPU and your RAM. And what will happen is the CPU will say, okay, I want to read this chunk, I want to read some memory, and it'll read a chunk into the cache. Now, hopefully, when the CPU is processing that data, all of the data we'll be dealing with is out of the CPU caches. So let's say our program is chugging along, we read some memory. Now in this case, we read this memory here, we got some allocated memory, and we happen to get some free memory too. These are read into the CPU cache. As our program is going along, processing the data in that memory, maybe it gets along to here, and it's like, oh, well, I don't need this stuff in the free memory now, I need a different address, I need to go somewhere else and get it. So unfortunately, what that means is maybe we have to hop over here and read out of there, and then continue with our program. Doing this hop and reading memory from RAM is a slow operation, so if we can reduce that, then we'll have a faster program. So if we're rearranging memory like this, hopefully we'll rearrange memory such that when we read out of memory, we'll read everything we need into a CPU cache, and we'll be able to process all the results. That is a feature, what do you call it? And the attribute of this is called good locality. If we have all of this data in the same kind of area, we call that good locality. Now, another good reason to compact is copy on write friendliness. At work, we use Unicorn as our web server, and Unicorn saves memory by using a copy on write technique. And compaction will increase the efficiency of this particular technique. So what this technique is when we create a parent process, and our parent process has some memory in it. So we boot up our Rails app, our parent process has memory in it. We fork off a bunch of child processes. Those child processes get a copy of the parent process's memory. So let's say we do this. We say, okay, we have a child process. Now, when the child process is created, it doesn't actually copy all of the parent's memory into the child process. Instead, it points at the parent process. So it creates virtual memory that points at the parent process. Now, let's say we need to write some data. The child wants to write some data into its pages. What will happen is the child process will say, okay, I want to write into a free memory chunk. It'll write into this free memory chunk, and that connection will get removed. So it's no longer connected to the parent process. So the child process will copy that chunk down into itself and then write into that location. Now, unfortunately, when this happens, the operating system takes care of this for us, and the operating system doesn't copy just what we need. It copies them in multiples of page sizes. So that means that instead of just copying that free chunk down into the child process, we may actually get some stuff on the left or right of it that we don't actually need. So instead, maybe we copy this allocated memory down into the child process as well. And that means now our child process is consuming more memory than we originally could have. So if we were to eliminate that fragmentation, it's less likely that we would encounter situations like this. So all of these problems are essentially, the solution to all of these problems is essentially eliminating fragmentation. And fragmentation, compaction is the solution to fragmentation. That's it. So just to recap, fragmented memory is memory that looks something like this. And when we compact it to have no fragmentation, it looks something like this. Now, another thing that I need to cover as well is that in Ruby, we can think of our programs as having two kind of heaps. So let's imagine we have our computer system. Our computer system has some amount of memory. Now, in that memory, when we allocate memory from the system, we typically use malloc to do that. So we'll create a malloc heap, what I call a malloc heap. So we ask malloc for memory, and we have some memory that's allocated via malloc. Now, inside of that malloc heap is Ruby's object heap. So we have two different ones, but one is inside of the other. So Ruby's object heap is allocated by malloc as well. But we can think of them as two separate areas. Now, whenever we allocate objects, those objects get allocated out of Ruby's object heap. So for example, we do object.new, that object comes out of Ruby's object heap like this. Now, ideally, the Ruby heap and the malloc heap would be exactly the same size, but unfortunately they're not, and I'll give you a simple example of why they're not. So let's say we have a string. We allocate a new string. This string actually points at a byte array, and that byte array is allocated out of malloc, okay? So the Ruby object that represents the string is allocated out of Ruby's object heap, but the actual string itself is allocated via malloc. This is one reason why the malloc heap will be larger than Ruby's object heap. Now, unfortunately, fragmentation can occur in both of these heaps. So when you talk about eliminating fragmentation, you need to be specific about which one you're talking about. So for the malloc heap, at work we typically use jemalloc, and I'm not going to get into this, but if you have a Rails application, you should use jemalloc or some other malloc besides libcs. For the Ruby heap, we use gc.compact, and that's the topic of this presentation. So Ruby's heap, let's take a look at Ruby's heap. And I don't mean the system memory or the malloc heap. I'm talking about what's stored inside of there. This is Ruby's heap. Ruby's heap layout looks something like this. Ruby's objects are represented by a fixed amount of memory. Each object is 40 bytes wide, right there. So one of these boxes represents a byte. Each object is 40 bytes. Each chunk is a slot. The slots can either be empty or filled. So we'll use white to represent empty and blue to represent filled. And later I'm going to introduce a new color, orange, and that's going to represent moved. Now, one page, these slots are stored on what's called a page, and one page is about 16 kilobytes. So here we have contiguous slots. These contiguous slots create a page. One page is 16 kilobytes, and our Ruby heap is made up of multiple pages. So this is what a Ruby heap looks like. So we have multiple pages here, and each of those pages is allocated using the malloc system call. Now, there's one more bit of information that we need to know before we can actually implement compaction, and that's that each slot in Ruby's heap has a unique address. So if we look at all of these slots, each of them has a unique address. Okay, so given this information, we can actually implement a compaction algorithm. So let's take a look at the algorithm that I chose. The compaction algorithm that we're going to use is called a two-finger compaction algorithm. This was originally done in Lisp. It is not a very good algorithm. And if we have time after this, I can tell you why, or just if you want to ask me a question, say, Aaron, why is this not a very good algorithm, and I will be happy to explain to you. But the reason I chose to do it is because it's easy to implement. And remember, when I first started this project, I didn't think it was possible. So I wanted to choose something easy to start with. So essentially, the algorithm has two different parts. One is moving objects, and the second part is updating references. First, we'll look at moving objects, and then after that, we'll look at how to update references. So imagine we have a heap that looks something like this. We've got a bunch of objects in there. The algorithm works by having two different fingers, or pointers, one to either side of the heap. One pointer is called the free pointer, and we'll put that at the left side. And the other pointer is called the scan pointer, and we'll put that at the right side. Now, the free pointer, it moves to the right until it can find a free slot. It'll go along like this, finds a free slot, and then it stops. The scan pointer, it will move to the left until it finds a filled slot. It'll go like this, and then stop. Once they're in place, it'll swap the two locations. So it just swaps like this. And then we leave a forwarding address in place of the old object. So here, this one was at 9, but it is now at 4, so we'll leave the number 4 here. Then we'll repeat this process. We'll move the free pointer over. We'll move the scan pointer back, swap the 2, leave a forwarding address, and then we repeat this process until the 2 pointers have met. So once the 2 have met, we are done moving objects around. The next part is updating references. So let's say we had that same heap. It looks something like this. This is before references are updated, or before objects are moved. Now, after objects are moved, it'll look something like this. And what we do to update the references is we essentially just walk through each object, looking at its references and updating them. So for example, we start by looking at 1. 1 points at 6, but it's fine. It's not a forwarding address. So we move on to 2. 2 points at, what is that, 9, but 9 is now at 4, so we update it to point at 4. So we say, okay, point over here at 4. And then we do that for 3 as well. 3 points at 8, but it should go to 5, so we update that. Thank you. And then we continue this process for each of the objects in the heap. And then we're done updating references, and all we have left to do is we convert those moved addresses into free slots, and we've successfully compacted the heap. This is it. So if we were to rewrite this algorithm in Ruby, this is a Ruby conference, not a C conference, right? Though I will give you pointers in C if you would like. Sorry. Okay. So this is what the algorithm would look like. Essentially, all we do is we say, okay, we're going to loop until the pointers have met, have the left and right pointer met. Right here, we have a chunk that says, okay, we're going to copy those, swap those two locations and leave a forwarding address. And then finally here, we'll advance the free pointer, and then we'll retreat the scan pointer. I didn't know what to call that. Opposite of advance, retreat, I'm not sure. Move them in opposite directions. Now, the next thing after we move everything, we update references. And this is the reference updating code. All we have to do is look at each object in the heap, check its references, see if they point at forwarding addresses. If they do, we'll fix them up. That's it. Now, unfortunately, this code, like if we look at this code, compare this to the previous slide, it looks like updating references is a very, very simple task. Like, this is pretty short code. Now, unfortunately, I was able to hide a whole lot of complexity in this slide right here. Slot.references. The question is, how are references stored? This particular method in this pseudocode is hiding a lot of complexity. So one task for this patch is to figure out how references are stored for every object. So for example, we need to know how do hashes hold references, how do arrays hold references, how do objects hold references, how do regular expressions hold references, structs, et cetera, et cetera, et cetera. Then once we know how all those references are stored, we can go and update them. So this is actually the most complicated part of this patch. So I'm going to show you the actual code here. Sorry, it's C code. This is it. One sec. Here is the entire patch. And that is only the reference updating part of this. If I was to estimate, I would say maybe 80% of the patch is just updating references. So since updating references is the most complicated part of this, I want to talk about this part of the project. This is probably the hardest part for me to implement. And the main thing is that we need to be able to update references while supporting C extensions. And I came up with a scheme for doing this, and I think that this scheme is the novel idea, which isn't, trust me, it's not that novel. We have to answer a question like, where are references stored? The most difficult thing about updating references is figuring out where all of them are stored. Now today, like, regardless of whether or not you have any Ruby core files on your computer, we are all part of the Ruby core team today, okay? All of us. Now, a nice thing for us, while we are all hacking on this garbage collector, is that we can say, okay, how does an array store its references? So, for example, we have an array here, and we can go look at the source code for array. And if we go open up array.c, we can see that the array points at a buffer. This buffer just contains a buffer of value stars, and this buffer just points at a bunch of different objects. So since all of us know how this is implemented, we can actually go into the garbage collector and say, okay, when it's time to update references for an array, we know how those references are stored, so we can actually go in and write the code to fix them up. So we can do the same thing for hashes as well. We know that a hash will point to a list of values and a list of keys. And we can look at the implementation of a hash. And since we all know the implementation of the hash, we can write the reference updating code. And we just repeat this process for every single class that's in Ruby. So we do it for strings, classes, modules, symbols, regexes, all of that fun stuff. So what I like to call these different types is I like to call these types known types. So the garbage collector can update all known types. Now, known types are types that are implemented by Ruby the language. But that leaves a question for us, what about unknown types? And I refer to unknown types as types that are implemented in C, and I'm going to give you an example of one. So we use a JSON parser called YAGL. YAGL is written in C, and it's a C extension. And this is the struct that's used for that parser. Now, you don't need to understand C to get this. I will explain it. But essentially, these two values here, the struct points at two values. These are Ruby objects. It has references to two Ruby objects. Okay? Now, when we create a new YAGL parser, we'll malloc this struct. So we do malloc, and remember, this is allocated out of the malloc heap. Then we'll also allocate a Ruby object. This is allocated out of the Ruby heap. This Ruby object will point at that malloced data, and this is the object that we deal with in our Ruby programs. Now, this struct here will also point, it has two references, as we noticed here in the struct definition. So it points at a builder stack and a parse compile callback. I don't know what those are. It doesn't matter. What's important is they're two Ruby objects. Now, unfortunately, the garbage collector doesn't know anything about this struct. So since it doesn't know the layout of this struct, it can't update those references. So how do we prevent those objects from moving? Now, the garbage collector will just look at this object and say, well, I don't know what this is, right? I can't fix it. Now, unfortunately, if any of these objects move, like let's say that one moves, now it's moved somewhere else, and the program will just crash. Hopefully. Yes. And just let me, I am going to convey to you how scary this is. So imagine, okay, hold on, I'm going off script here. Imagine that Ruby object moves, okay? So it moves, goes away. GC says, I don't know, this thing moves away. Now imagine the program continues to run, and it doesn't crash, like we don't use YAGL for a little bit. Another object gets allocated, but another Ruby object gets allocated, but allocated in its place. So now the reference is good, but it's pointing at the wrong thing. So just imagine that in your program. So yes, this is scary. So we really, really want to prevent this from happening. All right. So how do we do that? The way that we do that is all of these C extensions, they need to implement a mark function. They have to keep these references alive. If they don't keep the references alive, the garbage collector will, of course, collect them, and then the program will crash anyway. So C extension authors need to write a mark function that marks these references. And this code here is from the YAGL C extension. It's marking its references here. Now, what we can say is, we can say every time we mark something, the C extension author has to call rbgcmark, and they pass in the object that they want to mark, okay? So we can say, like right here, those two objects, they go through rbgcmark. And what we can do is we can say any object that's passed to rbgcmark, we will not allow it to move, okay? So anything marked with rbgcmark cannot move. That is our rule, essentially. In order to implement this rule, I had to add something called pin bits. And essentially what this is a bit table that sits alongside of the objects. So let's say we have an object layout that looks something like this. We got an array there at the top and a YAGL new. And I want to demonstrate the difference between a Ruby known type and an unknown type here. So during the mark phase, we'll go through and mark this. The GC will mark, YAGL will mark its two references with rbgcmark, and we'll mark those in the pin bit table. Now, when the array goes to mark, it'll mark its references, but it doesn't use that function. It uses a different marking function, one that we've implemented in Ruby and is private. So those two references get marked, but they don't get pinned in the pin bit table. Now, when the garbage collector goes to compact, we go and do the same algorithm. So we'll scan along, but what will happen is when the scan pointer finds something that's pinned, it just skips it and goes to the next one. So all the objects that were pinned, they don't move. And we just continue with this algorithm as normal, swapping, leaving, forwarding addresses, et cetera. Okay, great. Good job, Keynote. And it's that fast, too, the GC. So when we go through and update the references, the GC will look at YAGL and will say, well, I don't know this type. I can't update it. But it doesn't matter because we've guaranteed that all of its references stay put. They don't move. So it'll go and update the array. The array gets updated as normal. All the other objects get updated as normal. OK. Bleh. Thank you. That fast. So known types will use GC mark no pin. I've actually changed this to GC mark movable internally. I think it's better than no pin. Unknown types use RBGC mark, so we know not to move those. And this is how we can keep our C extensions safe, and this is the novel idea, I guess. So I want to talk a little bit about allowing movement in C extensions. So we would like to write C extensions that are compaction friendly. So what I did to do that is I implemented three things: compaction callback, movable marking, and a new location function. Now remember, the GC can't update C extensions, but C extensions, they can update themselves. So what I did is I said, OK, what we're going to do now is we're going to update YAGL to support compaction. This is the original implementation of YAGL. Here we specify a mark function and a free function, mark and sweep function. We'll update this to have a third callback, which is our compact function. So this is the updated code. Down at the bottom, we specify a compact callback. Now this compact callback gets called after every compaction. Now we change the mark function. Rather than calling RBGC mark, instead we call RBGC mark movable, and that essentially says, I want you to mark this, but it's OK if the object moves. Then inside of our compaction callback, we call this function RBGC location, and this essentially just asks the garbage collector, hey, if this thing moved, give me the updated address. And that's how we implement that. So there is one known issue, and this is kind of a doozy. So let's say we have an object graph that looks something like this. We have a Ruby object. It's implemented in Ruby, an object implemented in C, and they both point at the same object. But imagine that I am a C extension author, and I know that my Ruby object, it points at this third object, and I know that the C object also points at this third object. And I know that the Ruby object will keep this third object alive. So I think to myself, I am clever. I know that the Ruby object will keep the third object alive, so I'm not going to mark it from the C object. I will rely on that Ruby object to keep it alive. I know that this one is automatically marked via GC mark no pin, and I'm not going to mark this one because I know it's going to stay alive. Now, I don't know if some C extension authors did this on purpose or not, but it is a thing. So what will happen in this case is the compactor will run, we'll swap locations, everything will look just fine. The Ruby object, its references will get updated correctly, but the C object, its references will not get updated. It'll either point to a free location or, in a very, very worst case scenario, the wrong object. And our program will actually, hopefully, crash. We want it to crash in this situation. So maybe this isn't too common, although I have found it in a few places so far. One of them is the compilation process. When we convert text to an abstract syntax tree, this location has an issue. And I was able to fix it in most of these places. I fixed it in instruction sequences and the intermediate representation. We'll talk a little bit about that now. Essentially, inside of our instruction sequences, we point at real Ruby objects. So if you look at an instruction sequence is implemented in C, and it's an array of bytes, and it has a pointer at a live Ruby object, a literal in this case, a string. It used to be that we would keep these alive via a mark array. This mark array would be relied upon to keep those things alive. And of course, this particular pattern is almost the same as the one we saw in our problem object graph. So I fixed this by essentially walking all of the instruction sequences at mark time. And what that means is that we're able to eliminate this mark array and just directly mark these things. And as you can see, like, this is, to demonstrate that this has been a multi-year yak shave, this was actually released in Ruby 2.6 and was done in preparation of implementing this compactor. Now, essentially, the Ruby AST had the same issue. So during compilation, it would break, and I was able to fix that essentially in the same way. So there's direct AST marking as well, which you can look at the patch there. The intermediate representation also had this issue, and almost exactly the same pattern used there. I was able to fix that as well. So those are all in Ruby 2.7, so that is great. Okay, let's skip this because we're running out of time. Yay. All right, one more example. I found this in the JSON library as well. Now, an interesting pattern about this is that, this problem is that if these two objects are written in Ruby, we have pure Ruby implementations here. If we are clever, and by clever I mean evil, Ruby developers, we can actually cut this we can cut that reference because it's just Ruby code, right? And if we cut that reference, the garbage collector will go ahead and collect that object, and now we have a C extension that's pointing at nothing, and the program will crash. So let me give you an example. Here's a problem code here in the JSON library. We're pointing at constants, and these constants are actually globals. So somebody wrote global C nan and pointed that at the nan constant. Now, I could make this program crash by doing this. Essentially what I would say is, well, okay, guess what? I'm going to remove that constant here. The garbage collector would then go ahead and collect that constant when we did a gc.start, and then the program would crash. So that was cool. The fix is very simple. We just say we need to mark these things. I found the same issue in MessagePack. And again, since this reference was created in Ruby, I was able to cut it, make the program crash, and then, let's see if did I do the animation? Yes! Ah! I love that. I'm trying to use all of the Keynote animations. All right, so my hypothesis with this, and I think that most of you will agree with me, is that pure Ruby programs shouldn't crash, right? Yes, yes, please, yes, clap for that, yes. I know we all want to be on the Ruby core team, but our programs really shouldn't crash. We should not get core files out of them. So since I was able to get the rest of the core team to agree with this particular premise, and because of that, I could say, well, if I can make your program crash using a pure Ruby, it is a bug and we should fix it. Now, what shakes out of this is a very, very simple rule for C extension authors, and that is essentially, if you hold a reference, you must mark the reference. That's it. If you hold a reference, you need to mark a reference. Now, let me give you another solution. Another solution to this problem is to just don't write any C code. I think that that is the better solution. So let's go over one more challenge and then check out the results. I want to talk about object ID. This is an interesting problem when it comes to compaction. Now, generally, direct memory access prevents movement of objects. So let's take a look at how object ID is implemented in Ruby 2.6 and older. Object ID in Ruby 2.6 and older is actually based on the location of the object in memory. So this object here at position 1, it has object ID 1. The one at position 2 has object ID 2, et cetera, et cetera. Now, the question is, if one of these objects moves, what is the object ID now, right? And I'm going to talk about my initial solution for this, and we'll see a much better solution here in a couple minutes. Essentially, what I would say is, OK, well, what is the object ID after move here? In this particular example, it's very easy. We'll say, OK, the object ID here, we don't know. We haven't looked at it yet. So we'll compact the heap. It moves. We go check out the object ID. It is 1. That is great. No problem. So what is it after we move? We'll look at it here. We say, OK, object ID, check out, create an object, look at its object ID. It's 4. We compact the heap. But then we check the object ID again. Question is, what should the object ID be here? Well, you would probably expect 4, I would think. So to fix this, my initial solution was to keep track of that object ID, make sure that it didn't change. So essentially, I keep a global map. If you call object ID, we keep track of the object ID that you saw, OK? So essentially, the solution is here, walking through the code again, check the object ID, create a map, 4 maps to 4. We compact the heap. Now it's at address 1. So the address 1 maps to object ID 4. And when you call object ID again, you get the right number. Now, unfortunately, this introduces a problem, and this is a thing that sucks about this algorithm. What happens here, let's say we take a look at this, we move this, we allocate a new object. This object y happens to be put into slot 4. Now what? What should the object ID be? Well, in my initial implementation, what I did is I said, OK, well, we're just going to count up. Just add one. If that one's been used, we'll go up again. Just keep going. See what happens. And then store that. So in this particular case, our object ID is going to be 5. So let's walk through these animations. Yay. I can't wait to get to the better solution, because this one is not good. All right, so here we have object ID 5. Now, unfortunately, this means that we also have to clean up this table whenever an object gets freed. Otherwise, this table will grow forever. So in GC cleanup, we have to say, OK, when the object is freed, if the location was seen, we have to remove it from the map. So I call this mostly location-based object IDs, because it's typically the address, but sometimes it won't be. Now, fortunately, this is canceled. Well, it's like 20% canceled. Actually, we refactored it to be better. That's what we did. Now in master, I don't know if this is actually going to make it into 2.7, but in master, we actually have a monotonic object ID. And this, I worked on this with my coworker, Jay Hawthorne, so he is here. Say hi to him. But essentially, what we do is we say, OK, when you call object ID, we're just going to give you a number. And the next time you call object ID, we'll give you a bigger number. And we're going to do that forever and ever and ever and ever. And you'll always get a unique ID. So this is what it looks like if you build Ruby today. You call object ID new, and you just get a number. And it just keeps increasing. And you'll notice here, I gave an example here in the middle where we allocate an object, but you'll see each time it increments by 20. But that final one, that one in the middle there, it didn't get it. Right? It didn't get an object ID. And the reason I did that is to demonstrate that this number is only calculated at the time you call object ID. So a cool feature about this is that object IDs are truly unique. So before, since they were memory addresses, it meant that we could reuse them. That was possible. But today, they're unique. We can also do weird things like count the number of object ID calls. So for example here, the other thing we can do is, I didn't put a slide of counting object IDs, but I want to call something out here that's kind of weird. In Ruby 2.6 and older, if you call inspect, that hexadecimal number is actually related to the object ID. It actually is the address. Those two numbers are related. But now in Ruby 2.7 and newer, there's absolutely no relationship between those two numbers. And let's cut this part out of the video. But a question I have for you in the audience here is, if that inspect is based on the address and the object moves, what will the inspect look like? But please don't file a bug about that. Thank you. OK. So the TLDR here is, please don't use object ID. Unless you really need to, it's fine. So let's look at impact real quick. Oh my God, I'm way out of time. All right, so this is a basic Rails application. I've mapped the memory out. This is the very first implementation. This is after compaction. So that was before compaction. This is after. This is our Rails application at work. The top one is before compaction. Bottom one is after. It's way too big to fit on the slide, so I just slide it all the way over here like this. This is the very first implementation when I very first got it working. And this first implementation, 3% of the objects were pinned in the heap. I have since been able to improve it. I didn't tell you this. So red dots represent objects that are pinned. Black dots represent objects. White represents free space. OK? So the red dots, you can see from the red how much of the heap is pinned. So you can see we got a lot of it here. Even though what's kind of weird is that a lot is only 3%. So here is after some work on it, before and after. And you can hardly see any red now. So you can see it's shrunk down a bunch. That's with 1% pinned. And right now, this is what it is today. Actually, it may be even better than this. So you can see there we have a much bigger improvement. Oh, yes, thank you. 3% pinned, it results in a 10% smaller heap. Future plans, I'm way over time, so we're just going to do this. Future plans, I need to do performance improvements. It's not fast. It's very inefficient. We do a full collection, then move the objects, then update the references, then do a full GC. Though I've eliminated the full GC, that is gone. We still do these 3 steps, but we can reduce it down to 2, and it is theoretically possible to reduce that, combine those 2 together into 1. So I want to do that as well. In Ruby 3.0, my plan is to add automatic compaction. So right now you need to call gc.compact, but in the future you do nothing. The other thing I want to do is sliding compaction. The difference between what we have today and sliding is instead of using 2 fingers like that, we'll actually just slide them all together like that. And the reason I want to do that is A, for better locality, and B, it supports variable width objects. And the final thing that I want to do is implement variable width allocation. And what that means, oh, thank you, yes. What that means is today we have fixed width allocation that looks something like this. Our heap looks like this. Instead, I would like it to look something a little bit more like this, where we can allocate things of any size that we want to. So the way I want to end this talk today is we're constantly improving Ruby. The folks on the core team are doing their best to improve the Ruby implementation that we have now. I personally believe that Ruby's future is very exciting, and I want to say thank you to all of you for coming today. Thank you.